All right, so we're back here continuing to talk about pressure and fluid statics problems. And I've previously been looking at computing the net resultant pressure force on submerged shapes. And we looked at the general case of a flat plane that is submerged, and we considered how you would analyze the problem if it was tilted and if it was a arbitrary geometry. And now we're going to look at the case where the shape is curved. And these problems really are all about drawing and understanding how to use the right free body diagram. So that's what I have as a little blank here. This is the key thing to remember. That's why I leave blanks, is drawing the free body diagram correctly, and then you should be able to do the analysis from there. All right, and so the easiest way to understand how to analyze them really is to look at an example. The key idea is that we're going to make a vertical cut at the right point. In this case, it's going to be here at point A. And so if we're trying to figure out how much force is exerted on this curved shape, what we're going to do is we're going to cut the water right here, and then we're going to do a free body diagram on this chunk of water right there. And so what are the forces acting on that chunk of water? It has water on its left side that is pushing on it, and then it has gravity that is acting down. And then the shape AB is going to push on that chunk of water back in the other direction. So that'll have an X and a Y component to counterbalance those two forces. So that's really all we need to do, is to draw a vertical cut and then make the right free body diagram here. That's how we're going to do these. Okay, so I'm going to start by drawing this little quarter circle of water, and this could be some other shape, and the procedure is going to look pretty similar. And so we know that there's this pressure, distributed force here, and it's going to have a net resultant force on this piece of the water, and then there's going to be an opposing force in the X direction, and then there's going to be some weight from this big chunk of water down, and then it's going to have an opposing force in the Y direction. Okay, so to analyze this, it's pretty straightforward. You can analyze the X and Y independently. They don't really interact with each other, so you could do X or Y first, and I chose to do X first. So if we do some of the forces in the X direction, we have just the negative Fx, and then plus the average pressure times the area. So we looked at how you can get the average pressure from a shape like that. And again, in this case, the water starts at 0. The pressure is going to be 0 at the surface. But sometimes in these problems, when you draw that vertical cut, like if point B, if it was flat up here, then the pressure, like at this point, might be non-zero if you were doing an average. Okay, so if the water level was up higher above this, for example, at point B, then you would have to figure out the force on AB, you'd have to use the average across that section. All right, so that's not this problem, but that's how you would do it. So it's P average times the area of this shape here where it's pushing. And so we can then say that Fx needs to be equal to P average times A, and P average is just going to be 0 at the top, and then at the bottom it's going to be the depth here of 4 feet times the specific weight of water. So it's 0 plus 4 feet over 2. That's the average depth times the specific weight of the water, which is gamma. And then the area that it's going to be multiplied by is going to be 4 feet this way, and then we're told in this one the depth of this structure is 2 feet, kind of coming towards us, so it's times 4 feet and times another 2 feet. That's the area. Okay, and so then we know that gamma here is 62.4 pounds per cubic foot for water at its maximum density. You might use 62.3 there if you were to assume the water is something else other than 4 degrees Celsius, but I used 62.4. So if we then plug that all in, we get Fx is equal to 62.4 pounds per cubic foot times So this just becomes 2 feet here, all of that, and then times 4 feet times 2 feet. And then I got that Fx is equal to 997 pounds. Okay, so that's the force in the exerted on this structure in the x direction, and then in the y direction here, if we do some of the forces in the y direction, we have our Fy acting up, and then we have our weight acting down, and that it has to be equal to, I guess up here I didn't write that, but it has to be equal to 0 because it's not moving. Likewise down here, this has to be 0, and therefore we have Fy has got to equal to the weight, and we know that the weight is just the specific weight times the volume. Okay, the weight is the specific weight times the volume of that shape. So we need to then just figure out the volume of that shape, and we can do that. And so in this case, the geometry of this shape is a quarter circle, and so the volume is going to be pi r squared, where this is r divided by 4 because it's a quarter of that, and then times the thickness here into the page. Okay, so we have Fy is equal to then 1/4 of pi r squared times, if we call it like t into the page, and then times gamma, and so it's just 1/4 pi times 4 feet squared times 2 feet thick into the page, and then times 62.4 pounds per cubic foot, and therefore we get the Y force is 1,565 pounds. So that's the net resultant force in the X and Y direction. And you could then figure out the net force here and the angle. I'm not going to bother with that because we're worried about fluids here, and that's something that you should have plenty of practice on in a statics class. So this is how you can analyze the net resultant force on a submerged shape that is curved.